The normal distribution. Examples of using the normal 0, 1 table. Suppose z is a random variable with a standard normal distribution. Find the probability that z is greater than 1. Remember that the cumulative distribution function provides the probability that z is less than or equal to something. In the figure below, we're asked for the area of the region shaded yellow, which is, of course, 1 minus the area of the region shaded green. And that is provided for us by the normal cumulative distribution function. In other words, the probability z is bigger than 1 is 1 minus the probability that it's less than 1. 1 minus 0.8413, which we found in the normal table. What if we want the normal cumulative distribution function evaluated at a negative number, like minus 0.5? Find f of minus 0.5. Since the normal density is symmetric about the value 0, the probability in normal random variable x is less than 0 minus 0.5 is identical to the probability that it's greater than plus 0.5. And we've just discovered that we can find the probability x is bigger than 0.5 as 1 minus f of 0.5. 1 minus 0.6915 in this case. What do we do for negative values of x? By the symmetry of the standard normal probability density function, the probability that x is less than or equal to minus x is exactly the same as the probability that x is greater than or equal to plus x, which is to say that f of minus x is equal to 1 minus f of x. The CDF for negative values of x is determined by looking at the entry corresponding to the positive value of x and subtracting this from 1. Standard normal probabilities. Here's an example. Find the probability that a standard normal random variable z lies between minus 1 and plus 1. In the figure below, we're looking for the area shaded yellow under the density function, the area between minus 1 and plus 1. And that is, of course, f of 1 minus f of minus 1. If we replace f of minus 1 by 1 minus f of 1, this turns out to be 2 times f of 1 minus 1, or 0.8413 minus 0.1587, both of these numbers found from the table, or about 68%. Do the same replacing 1 by 2. What's the probability that z lies between minus 2 and plus 2? In other words, what's the probability a normal random variable lies within 2 standard deviations of its mean? This is the area shaded yellow in the graph at the bottom of this slide, f of 2 minus f of minus 2, and by a similar calculation, that turns out to be 0.9544, a little more than 95%. And if we repeat and calculate the probability that z is between minus 3 and plus 3, you can see from this figure that includes most of the area under the density. Indeed, it's 0.999 minus 0.001, somewhere around 0.998, 99.8% of the area. Almost all the time, a normal random variable falls within 3 standard deviations of its mean. Review question. Suppose z has a standard normal distribution. Use the tables to find the probability that the absolute value of z minus 1 is less than 3. Find this probability to 3 decimal places. You're given several choices A, B, C, D, and E. And the first thing you should do is visualize the density function. Z minus 1 in absolute value less than 3 corresponds to the values of z that lie between minus 2 and 4. And if you imagine that interval on a normal density, then it would cover most of the density function, omitting only a small fraction below minus 2, which is to say that the solution should be pretty close to 1. Formally, the probability that z minus 1 is between minus 3 and plus 3 is the probability z is between minus 2 and plus 4, f of 4 minus f of minus 2, since f of 4 is approximately 1, 1 minus f of 2, where we've replaced f of minus 2 by 1 minus f of 2. And again, consulting the table to find the value of f of 2, we see it's 0.97725. Doing the arithmetic gives us an answer of 0.97725. To 3 decimal places, 0.977. The correct answer was C. Here's some verification of important properties of the normal density that you might work through, including the fact that the density function integrates to 1, as does every density function. The integral from minus infinity to infinity of 1 over the square root of 2 pi sigma, e to the minus 1/2 x minus mu over sigma, the quantity squared, is 1. Now, the first step in the solution here is to change variables to a variable we've called z. Z is x minus mu over sigma. When we do that, the integral looks much simpler. The integral from minus infinity to infinity of 1 over the square root of 2 pi, e to the minus 1/2 z squared. And since the integrand is symmetric about 0, we can replace the integral from minus infinity to infinity by twice the integral from 0 to infinity. And one more change of variables. Replace 1/2 z squared by the variable y, which converts the integral we're interested in to 2 times 1 over the square root of pi times the integral from 0 to infinity y to the minus 1/2 e to the minus y. And this may look familiar. That's a standard integral. In fact, it's such an important integral. It occurs so often, with various powers replacing 1/2 or minus 1/2, that it's called the gamma function. Indeed, that integral is gamma of 1/2. So we're left with 1 over the square root of 2 pi times gamma of 1/2. And since gamma of 1/2 is equal to the square root of pi, we end up with a total integral of 1. The expected value of a normal random variable. Suppose x is a random variable which has a normal distribution with mean mu and variance sigma squared. Then the expected value of x is equal to mu. Well, let's verify that. The expected value of x minus mu is obtained by integrating the quantity x minus mu multiplied by the density function. And so you'll see next to that the normal density function in its general form with mean mu and variance sigma squared. Now, this calls for another change of variables. This time we're going to let y be x minus mu. And the integral simplifies to the integral of y times a constant, 1 over sigma square root of 2 pi, e to the minus y squared over 2 sigma squared. And the advantage in this form is that it's now written as y times a function of y squared, e to the minus y squared over 2 sigma squared. That function is symmetric about 0. So y times that function is odd. I've called that product g of y here. It's an odd function, meaning that its value at minus y is the negative of the value at y. G of minus y equals minus g of y. And when you integrate an odd function from minus infinity to infinity, the negative values are cancelled by the positive values, and so the total integral is 0. That means that the expected value of x minus mu, according to this calculation, is equal to 0. And since e of x minus mu is equal to e of x minus mu, it follows that the expected value of x must be the constant mu.